Hey everyone, and welcome to this explainer for the Foundry by Forge College. So, as part of our broader Applied Solidity development track, we're currently working through the Access Control Patterns module. Specifically, today we're introducing the Pausable pattern. Now, if you were with us for our last lesson, we completely wrapped up the tricky business of version control and debugging for your deployment scripts. You know the feeling, right? Your code is pristine, your tests are passing with flying colors, and your deployment went off without a hitch. But today we need to talk about what happens after deployment. We need to figure out exactly what to do when your absolutely perfect live code suddenly goes completely haywire out there in the wild.
Picture this scenario for a second. It's mainnet launch day. You're sipping your morning coffee, feeling like an absolute Web3 rock star. But then you glance over at your monitor and you see your smart contract's total value locked just dropping. And I mean dropping fast. Maybe someone found a zero-day bug, or maybe some totally unexpected external condition triggered an exploit. Either way, your perfectly written code is just sitting there, diligently processing transaction after transaction, literally draining your protocol dry. Let me tell you, in that terrifying moment, staring blankly at your screen, you do not need a debugger. No way. What you need is a panic button.
Okay, let's dive into this architectural blueprint. Today, we're covering 5 key areas. First, the smart contract circuit breaker. Second, the mechanics of the pause. Third, designing your pause scope. Fourth, token transfers in practice. And fifth, wrapping up the pattern. Let's get right into it.
All right, section 1, the smart contract circuit breaker. Basically, this is an emergency stop for your code.
When we talk about the circuit breaker concept, we're looking for a highly pragmatic defense-in-depth control. Listen, the goal here isn't to somehow fix the bug on the fly. That's basically impossible. The goal is to drastically reduce the blast radius while you figure out what the heck went wrong. And that brings us directly to the definition of the pausable pattern. At its core, it's incredibly simple. It's just a boolean flag, a true or false state variable that acts as your emergency stop, freezing selected operations during an exploit. Now, you already know how to protect critical functions using modifiers like onlyOwner, right? Well, the pausable pattern acts as an additional safety layer that sits right alongside those existing ownership and role checks.
So the crucial point here is really understanding the difference between access control and pause control. They're related but very different. Access control dictates who can call a function. Think of your classic onlyOwner modifier. Pause control, on the other hand, dictates whether a function is allowed to run at all, entirely independent of who is actually calling it. We usually implement this with a modifier like whenNotPaused. It beautifully separates two completely orthogonal concerns in your contract's architecture.
To make this intuitively obvious, just think of the electrical circuit breaker in your house. A breaker trips when the current exceeds safe levels, right? It isolates the fault to prevent your house from catching on fire. But here's the key takeaway. You don't shut down the power to the entire building just because a single light bulb flickers in the hallway. You isolate the specific, risky circuit. And honestly, this mental model is exactly how you should be reasoning about smart contract pauses.
Moving on to section 2, mechanics of the pause. This is all about how we actually wire the switch in Solidity.
So we know what a pause is conceptually, but how do we actually build this infrastructure inside our code? It essentially boils down to 3 sequential engineering steps. Step 1, you add a boolean pause state. Usually we just call it paused, and you expose functions to change that state, like pause and unpause. Step 2, you wrap your highly sensitive code paths with modifiers. You'd apply that whenNotPaused modifier to things like token transfers or asset withdrawals, ensuring they automatically revert if the flag is ever flipped to true. And step 3, actually pause here, because developers forget this one all the time. You absolutely must emit clear events on these state changes. Off-chain monitors, indexers, and user interfaces need to know that the breaker tripped so they can react and warn users rather than just silently failing in the background. Section 3, designing your pause scope. Because granularity is absolutely key to minimizing damage.
Remember that circuit breaker analogy we just talked about? Well, granularity is your best friend here. Separating functional domains like, say, transferring tokens versus minting new ones keeps collateral damage to an absolute minimum during an incident. If you get the scope wrong, you face 2 pretty extreme failure modes. On one end, we have the stuck open breaker. This is a contract that gets paused and literally can never unpause. Sure, your protocol is perfectly safe, but unfortunately, it's now a brick. You've lost all availability. On the exact opposite end, you have the stuck closed breaker. The breaker just refuses to trip, meaning you never pause, leaving you wide open as an all-you-can-eat buffet for attackers. You need careful monitoring and super clear recovery paths built directly into your design to avoid both of these embarrassing extremes.
Up next is Section 4, Token Transfers in Practice. Let's evaluate some real-world ERC20 pause scenarios.
Let's ground this in reality for a minute. Without a pause mechanism, a vulnerability in standard ERC20 functions like transfer or transfer from can just be exploited continuously. And this brilliantly illustrates the trade-offs we have to make in our scope. Look, if you implement a global pause, all state changes revert. You get maximum safety but zero availability. This is usually controlled by a multi-sig or a governance vote. But what about a transfers-only scope? Well, this blocks everyday token transfers but might still allow critical administrative tasks like emergency withdrawals. Or consider a minting-only pause. This stops token creation entirely but actually lets the secondary market continue trading without any disruption. At the end of the day, choosing the right scope depends entirely on your protocol's specific threat model and what your users expect to happen during an emergency.
And finally, Section 5, wrapping up the pattern. Let's cover the final rules for your architectural blueprint.
As you continue to expand your Web3 knowledge, you're going to find that Forge College's wider programs heavily emphasize these exact architectural best practices, because it's not just about making code work, it's about making code resilient. Let's rapidly summarize our key rules. Rule 1. Separate access control, who calls, from pause control, whether it runs. Rule 2. Limit your collateral damage by using granular domain-specific pauses. Rule 3. Balance speed and oversight. Tripping the pause should be fast, maybe a rapid response multisig, but unpausing should require real oversight, like a time lock or governance vote, just to prevent any malicious resumptions. And Rule 4. Always omit events and have a well-documented recovery path. Mastering these rules perfectly prepares you for our next lesson, which is all about designing emergency stop strategies.
Which leaves us with this final, provocative thought to chew on today. When disaster strikes your protocol, who exactly controls your panic button? Is it a single admin, a decentralized autonomous organization, or maybe a specialized security council? It is a massive governance question, and it's one you absolutely have to answer before you deploy to mainnet. I highly encourage you to visit forge.college to dive deeper into this subject, explore the different controller strategies, and check out all our other Web3 related topics. Thanks so much for joining me on this explainer, and I'll see you in the next one.